In the previous video, we took a look at the nature of sound waves. We learned that sound waves are just pressure waves with regions of compressed and rarefacted medium, represented by crests and troughs in a wave, respectively. We also discussed how to describe waves using parameters such as amplitude, wavelength, period, frequency, and intensity. In this video, we're going to further explore the properties of waves. Waves can be reflected, refracted, and absorbed. We will also learn that two or more waves can interact with each other through a process called interference. We will end this video with the concept of resonance, a phenomenon that happens when waves interfere in a closed surrounding. Several things can happen to a sound wave as it travels through a medium. Sound can be reflected, absorbed, or transmitted. An echo is evidence of sound being reflected. Sound intensity decreases with distance because part of the energy is absorbed by the air molecules as the wave travels. When sound passes from one medium to another, the outgoing sound is transmitted. If you've entered a room with no furniture, then you'll notice that when you speak, you hear your voice clearly and your voice comes with an echo. But as soon as you add furniture to the room, then the echo disappears and the intensity of your voice becomes less and less. That's because the furniture absorbs the sound waves you generate. Tie one end of a long string to a wall and then hold the other end. You can generate a wave along the string by simply shaking the hand holding the rope back and forth. Notice that the waves travel along the rope and it's reflected at the other end by the wall. That's the wave being reflected. Sound waves are reflected in precisely the same way. There are so many examples in nature, in our surroundings, and in our technology that utilizes the reflective nature of sound waves. One common example is a bat's ability to locate objects using sound. This is called echolocation. In this video, you will hear bats producing sound and listening to the sound waves reflect against its surroundings to look for food. Dolphins use the same echolocations, producing sounds and listening to the sounds reflected by their surroundings. Their echolocation abilities are so finely tuned that they can distinguish between the different animals or different objects in their surroundings in precisely the same way we distinguish them using our eyes. This table shows the refraction of the sound reflected and transmitted at tissue interfaces. For example, between air and muscle, 98% of the sound is reflected and 2% is transmitted through the muscle. Between air and water, 99.89% is reflected and only 0.11% is transmitted. Bats and dolphins are able to distinguish between these reflected waves and are able to tell whether the sound is reflected off a muscle or water. Submarines and ships use the same principle to get a good view of their surroundings. Sonar means sound navigation and ranging. It sends out sound pulses and listens to the sound reflected from its surroundings. Sonar is not as accurate as nature just yet and is unable to distinguish between the types of fish in the ocean. Here's the sound of a whale producing sound from underwater, and we hear the sound in air. Sound travels from water and is transmitted to air. This is called refraction. Refraction happens when waves travel from one medium to another. For sound waves, the speed of sound changes as well as the wavelength of the sound. The frequency remains the same. That's why we hear the same notes underwater or in air. Have you ever noticed that at night you hear sound so clearly even at faraway distances compared to during the day? It's not because it's quieter at night. It's because sound is refracted. In the morning, warm air is nearer to the ground than cold air. Recall from our previous lesson that the speed of sound depends on temperature. So sound traveling through the warm air travels faster than sound traveling through the cold air. This causes the sound wave to bend upwards, and therefore you don't hear sound as much as during nighttime. At nighttime, the cool air is nearer to the ground than the warm air, and as a result, the sound wave bends downward towards you, the listener. Thus, the sound is louder and clearer during the night. The third thing that can happen to sound energy is that it is absorbed. The reason why sound decreases with increasing distance is because sound energy is already absorbed by the air molecules. Not as much though as some solid materials. Let's take a look at how sound absorption in materials work. You can see that the use of proper materials combined with good design can provide very good sound absorption. We've now learned that sound can be reflected, transmitted, and absorbed, and it happens all the time, with each sound wave reflected, transmitted, and absorbed in varying degrees. So far, we've discussed sound waves with the impression that it's only produced with one frequency. In reality, when you talk or when you sing a note, it's composed of many frequencies. The main frequency is called the fundamental frequency or the first harmonic, while the rest are called the overtones or the harmonics. What you're seeing now are the frequencies measured by a spectrum analyzer corresponding to my voice as I am speaking. The yellow lines are the real-time measurements of the frequencies. The baseline, when I'm not speaking, is just ambient noise or noise from the surroundings. The pink line is just an average based on past measurements, and it dies down eventually. You'll also see the real-time intensity level indicated by the arrow and the orange digits. Let's try some notes. As I whistle, you'll see peaks corresponding to the fundamental frequencies and the overtones. While I whistle, take a look at the table corresponding to the different musical notes and see if I hit the right notes. Did I hit the right notes? Let's check the key of C, specifically C6 or soprano high C. It corresponds to 1046.50 Hz. In the spectrum analyzer, the note my whistling generated had a fundamental frequency of about 1100 Hz. The first overtone or second harmonic of C6 and my whistling has a frequency of about 2200 Hz. So I'm quite near to hitting the exact notes. Whenever we talk, sing, or produce any sound, the sound that we produce will always have many frequencies. Why is this? Let's take a look at this clip. In this clip, the person is going to produce the fundamental frequency and the second to fifth harmonics by simply shaking one end of the string at a specific frequency. He's going to do the fundamental frequency first, and then slowly increase the frequency of his hand vibration to produce the harmonics. The first harmonic is actually 1/2 of a sinusoidal wave, as you can see from the vibration and from the figure. So it's 1/2 the wavelength. And from the clip, 1/2 of the wavelength is exactly the length of the string. The second harmonic is equal to 1 wavelength, which is exactly the same as the length of the string. The third harmonic is 3/2 the wavelength and is again equal to the length of the string. So you can work out mathematically that n/2 times lambda sub n is equal to L, where n is equal to 1, 2, 3, or the harmonic. Since the wavelength is related to frequency, you can easily work out the frequency of vibration to be f sub n equals v sub s over lambda sub n, or equal to n times v sub s over 2L. The waves that are formed are called standing waves. They are formed because the wave that is reflected at the other end of the string adds up with the wave that moves toward the end of the string. To understand interference, let's first draw a wave. This is a wave with a frequency of 100 Hz. This means that its period is 1/100 seconds, or 0.01 seconds. Let's draw a second wave with the same frequency, but shifted by half a cycle. If we add the black wave to the black wave, we get the same wave, but with twice the amplitude. If we add the second wave to the second wave, we also get the same wave with twice the amplitude. These are examples of waves interfering constructively. If we add the first wave to the second wave, we get no wave at all, as shown by the blue line. The two waves cancel each other out. The blue line is the sum of the black and the red waves. In this case, we say that the two waves interfered destructively. Let's animate the interference between waves. What's going to happen is that the red line will move towards the right. The blue line is the sum of the red and black waves at any time. You'll see that when the black and red waves exactly coincide, they add up or interfere constructively. And when they are shifted by a half cycle, they cancel each other out or interfere destructively. This type of interference happens quite often in nature. Water waves are the most common source of waves interfering with each other. It is possible to take a look at the interference in sound waves using what's called a Schlieren effect. This is the same effect used to measure the pressure waves around the bullet as it speeds through the air. What you see is air being compressed as the bullet passes, and it's because of the strobing effect of light that you can see the compressed air around the bullet. Now let's take a look at sound waves at a frequency of 28 kHz generated by speakers. Remember, what you're looking at is the air surrounding the speakers because of the strobing effect of light. What you watch are examples of interference of water waves and sound waves. Let's take another look at this video. We see the forward moving wave and the reflected wave. If we add both waves together, then we get these standing waves. The harmonic will depend on the frequency of vibration. Standing waves happen when waves are confined, such as in this case, where the wave is confined between the hand and the wall at the other end of the string. Because they are confined, waves travel back and forth and interfere with one another, forming standing waves. Let's take another look at another type of confined wave. The video shows how the sound waves pushes the glass rim to vibrate. Since the vibrating glass is confined, it also forms these standing waves. We also say that the glass is resonating with the frequency of the sound or is in resonance with the sound wave. This is why when you flick the wine glass by the rim or rub the rim, it will produce a sound. The rim is vibrating, producing the sound wave that we hear. The frequency corresponding to that sound is the resonant frequency of the glass. That resonant frequency is typically within our hearing range, which means that it's also possible to break a wine glass just by singing at the correct note and with sufficient loudness.
You want to be able to reproduce that tone as loudly, as accurately, and for as long as you can. I like to sing it right there, so I'm putting my mouth right there, not in the glass and not at the bottom like that. The only way to be able to sustain that note that loud for that long is to practice. It took me a while. That's how you do it.
In today's lesson, we've talked about the other interesting properties of waves. These are reflection, refraction, or transmission, absorption, interference, and resonance. We've seen how these properties work in nature and in existing technologies. These concepts are available for you to read in our reference material in greater detail. At the end of the video, you'll see sample exercises related to this topic. I've added the full videos of the clips presented in this video lesson in our VLE, plus a couple more. Feel free to watch any of them if you like.